Hey, welcome. My name is René Schulte. I'm Director of Immersive Experiences at Identity Mine, and I'm also Microsoft MVP for Windows development. And I have a background in computer graphics and virtual reality and augmented reality and those kind of things since many years, actually. I have a few open source projects. One of them is an AR Toolkit port. And it was like a few weeks ago when I had the 5-year anniversary when I was porting this AR Toolkit port over to Windows Phone Mango. Does anyone remember Windows Phone Mango? Yeah, you're my man. That was a good time, right? So they finally added like camera access API, so I could do some computer vision with that stuff. But that's history. Now we're talking about HoloLens. And today I want to speak about HoloLens development we have been doing since actually last year. So first I want to set some terminology straight. What is VR, what is AR, what is MR, because it's often mixed up. Then I will tell you a bit about the HoloLens device. I have the current development kit here with me. And then I will tell you how you can develop for it. We will do a nice demo using Unity from scratch and build a nice little game or app, if you will. Yeah, and then at the end I want to spend some time to okay? Yeah, and at the end I want to spend quite some cool, awesome. Yeah, give a good hand for the technician. So yeah, let's get started. And at the end, I want to talk a bit about the experience and about the things we learned while building HoloLens apps since a couple of months, or since last year actually. A few words about the company I work for. Identity Mine is headquartered in Seattle in the United States, but I actually work out from Dresden in Germany. Identity Mine has always been at the bleeding edge of technology, so I've been working with those big multi-touch tables, those pixel-sensed tables. We're doing Xbox One, Xbox 360 apps, Connect for Windows. We have actually Connect for Windows solutions deployed in the real world, not just for, try out, but actually real use cases. And we were also bought by an early program from Microsoft for HoloLens, so we're developing for HoloLens since last year. Here's a quick video I want to show you about the company. It's just 1 minute. It shows some of our HoloLens stuff we're building, so I think it's worth it. Okay, enough of the marketing. Let's talk about some content. So what is virtual reality? Virtual reality is a fully immersive multimedia solution, which means you're fully inside a computer-generated world and you don't see the outside, the real world anymore. And virtual reality is around since many years, actually, think about flight simulators, so many decades, actually. But now we have consumer devices that are available for the masses, and we have on the low end like Google Cardboard, and in the high-end spectrum we have devices like the Oculus Rift and the HTC Vive, which are not too expensive compared to what we have like 5 or 10 years ago, and they provide a very good quality. And with quality I especially mean latency, because latency is a big challenge with those VR headsets, because what you want to do is you want to render the scene very realistically. And on the other hand, you also need to provide it as a fast feedback. So when the user rotates the head, you need to quickly render a new updated frame and send that back to the device to show it to the user. So this is the latency. And with VR, we're talking about 3 milliseconds. So actually, anything that's taking longer than 3 milliseconds can make a user sick. They can throw up, they can get headaches, and other things you probably want to avoid for users. Also important is we humans don't just have eyes, right? We also have ears, we have hands, and so on. So spatial sound is something that those devices already implement, and there are also like those data gloves, which have those little motors inside where you can give haptic feedback. And there are even experiments with virtual smelling, which could be fun, but could be also very awkward. I'm thinking about the VR thought app there, right? This will happen, I'm sure. So what is AR? What is augmented reality, and what is mixed reality? On the other hand, it's not fully immersive. This is clear. So you still see the real world. You don't just see the virtual world. You see the real world, which is augmented with virtual objects. So this is the main difference compared to VR here. And the Microsoft HoloLens I have here is called a mixed reality device, although it's actually also an augmented reality device. It seems like everyone has its own definition what mixed reality means, right? So, but I just want to tell you why Microsoft calls it mixed reality in order to diversify from the existing augmented reality solution we have these days. So you probably all have a smartphone with some kind of AR app on it, with an augmented reality app. And what they do usually, they take the camera stream, they analyze the camera stream, run some computer vision on of that, and then augment that with virtual objects, and you see the real world not with your own eyes, but through another screen. You see that also monoscopic, because the camera is monoscopic. It's a cyclops, basically, just one eye. So you don't see it stereoscopic, and you see it through another screen. But with the HoloLens, you see it with your own eyes. It's mixed, basically, because you have those nice see-through lenses here, where you can see the real world with your own eyes, and then the virtual objects are faded in there. So Microsoft wants to diversify, kind of, so they call it mixed reality. Challenging, it's even more challenging to have low latency, because you also need to analyze the real world. You don't just generate virtual objects, but you also need to run the computer vision, basically. So even more challenging to keep a good frame rate there. And of course, you want to seamlessly merge the real world with your virtual world, and this is quite challenging if you want to have realistic rendering. Cool, so let's talk about the HoloLens. And I have the current development edition here with me. The HoloLens is a mixed reality head-mounted device from Microsoft, and it has a bunch of sensors integrated. So it has an IMU unit, an inertial measurement unit, which is basically used for the head rotation, right? Then it has a bunch of cameras like those here. Those are environmental cameras, which basically scan the room. They are used to provide a spatial mapping of the room. So this is nice. We will use that in a demo later, where we use the spatial mapping of the room, so to bounce some physical objects off. It has an RGB camera, it has a depth camera. What else? Microphone array. So it has a bunch of microphones here, which are used for speech recognition. It does a very good job for speech recognition. Yeah, and everything is self-contained. So the device contains everything inside here. It's actually a computer. It's not just a display, it's a computer. Because there's a CPU in here, a GPU, and a new coprocessor Microsoft calls the HPU, the holographic processing unit, which is basically responsible for doing the spatial mapping, speech recognition, gesture recognition, and so on. Yeah, and another cool thing is actually multiple people can wear a HoloLens and they can see the same holograms. So if you would all have a HoloLens, you all get one from me. I'm just kidding. So if all would wear a HoloLens, we could basically see each other, right? This is also a nice diversification factor compared to VR, because with VR just on your own world. With AR, you still see the real world. So multiple people can wear the HoloLens, they can see each other, they can still see the room, and they could also see the same holograms. So this kind of multi-lens collaboration feature is a very, very nice, unique point of the HoloLens. And it's a Windows 10 device, so you can even pin your Microsoft Edge browser tabs on your walls and stuff like that. Cool, so what is the input and output paradigm of the HoloLens? The HoloLens uses the so-called GGV input paradigm, which stands for gaze, gesture, and voice. So when I wear a device like this and I rotate my head, this is where I'm looking at, right? So this is where I'm gazing. I'm basically setting a gaze vector, a ray. And this ray is giving me the interaction focus. So this is where I know, okay, this is where the user is looking, this is where he's interested in. So think about in the desktop world as a mouse move, basically. And the next thing is the air tab. So I can have a couple of different gestures, and one of them is the air tab gesture. So I hold my index finger up like this, and then I tap like that. So this is, in your desktop world, the mouse click, basically. So you're gazing, setting the interaction focus, then air tapping to trigger the actual action, like a mouse click, if you will. And since this is quite limited in terms of input, voice and speech recognition is a very important natural user interface input mechanism for HoloLens as well. And it does a very good job. It's actually better than Xbox One speech recognition. It's using Cortana inside its Windows 10, like I said. For output, you have those two see-through lenses here. Each of them has 1 megapixel resolution. And it's actually not just a simple flat screen or flat lens. It's actually multiple layers. So the camera, the stream is split up into the channels like red, green, and blue. And each of them is fed into each layer, basically. And spatial sound, and we will talk about spatial sound in a second later. Those tiny speakers provide a very good, nice spatial sound, which is an important addition to the visual aspect. So how can you develop for HoloLens? First of all, you can just use Direct3D directly, Direct3D 11 with C++, or even SharpDX, which is a wrapper around Direct3D and C#. Or you can use a middleware like Unity. And Unity is not just a 2D or 3D game engine where it comes from, it's actually also used to build applications. And you have a ton of amazing components already available, like a very good global illumination system where you can have very realistic shading and also physics and so on. Yeah, you have this nice high efficient workflow. You can be very productive with Unity and develop quickly using Unity. And of course, it's cross-platform. They have right now 28 platforms they support as target output, which is pretty impressive. They have built-in VR support since a few versions, so the Oculus SDK is integrated already, so you don't need to install a separate plugin to Unity. You can just use it right out of the box. And Unity is a first-class citizen for HoloLens development, that's for sure, because Microsoft puts out all the tutorials, and the Holographic Academy, it's all built using Unity, basically. And actually, a few of the applications you find in the Windows Store for HoloLens are also built by Microsoft, and they are also using Unity for a few of them. So you can build some real cool stuff. And yeah, it's still free for personal use. So I was at the Unite conference last week in Amsterdam, and they announced a different pricing model for the professional and the plus version, but they're still keeping the personal version for free. So you can use the free version for non-commercial use case, and you can download the SDK for the HoloLens, the emulator, and Unity, and all of that for free, and can get started. It's pretty nice. Cool. Enough talking. Let's build something, right? What we will do, I will start with a fresh new Unity scene, and I will configure it so it can be deployed to the HoloLens, and we will implement the things we just talked about, like gazing, gestures, spatial mapping, and speech input. And we will do this with a nice little setup of physics objects. So we will have a nice plane. We stack some cubes on top of that, and then we can shoot a sphere from the camera, which is the user's head with the HoloLens, basically. And we can shoot spheres into the scene, and they will bounce off physically correct, basically. So let's switch to Unity. So this is Unity. You probably have seen it. I don't want to go too much into detail about Unity here. Brian had a nice session yesterday about it. So, but this is basically your scene view. You have the hierarchy of the scene here, and this is the game view, and this is the assets view where you see all your files. So first thing we need to configure for HoloLens is the main camera, because if we have a fresh new Unity scene, the camera has a set position of 0, 1, and -10, which can cause an offset if we use it for the HoloLens. Because like I said, if the user walks around with the device, the position of the device is mapped to the main camera in Unity, right? So we don't want to have an offset here, so we set it to 0, not 10, 0, 0, 0. And also the head rotation is mapped to the camera rotation. Okay, so we set this. The next thing we need to set is a solid color black as a clearing flag, because every frame we want to clear the frame. And the HoloLens uses additive blending, which means the virtual objects are blended into the screens using additive blending, which means black is transparent. You cannot see black with the device. So we clear it to black, and we set the near clipping plane to 50 centimeters, because we want to avoid that the user's eyes are crossing, basically. So if the virtual objects are rendered too close to the camera, the user's eyes will start to cross, which is also uncomfortable. So we want to clip off the rendering at 50 centimeters or 80 centimeters. And we also don't need 1,000 meters, we need 10 meters. And you notice it's all in metric space, right? This is also nice with the HoloLens. All the spatial mapping is already in metric space and in the real world scale. Cool. So we have our scene set up here. And now let's also enable the player settings for HoloLens. We can find them here. And we need to switch to this tab, which is Windows Store Applications or Universal Windows Platform. And we need to enable just this checkbox. So the Windows Holographic SDK is included in our target output. Another thing we need to set is the publishing settings. And if you've done UWP apps before, you probably are familiar with those capabilities. And we need to enable some checkboxes here. Internet client, because we want to use the emulator also for a bit, which is connecting with the hosting operating system. Also microphone, since we want to use speech recognition. And spatial perception, since we want to use spatial mapping. Okay, so we have everything set up. let's actually add some objects. What I usually do, I create an empty game object as container where I can place objects that are belonging in the same physical location together and group them. And I will tell you at the end why I do this and why it makes sense. So reset the position and set it a bit further away from the camera. So we set it like 50 centimeters lower and 2 meters in front of the camera, which is usually a nice way when you start an application that the holograms are starting like 2 meters in front of the user's view. Cool. So let's add the plane I mentioned. So this is our plane. A bit too large, so let's reduce the size here. And like this. And yeah, we want to have a different color. So we create a material, and since we're good citizens, we create a folder for that. So let's add a folder for materials. And yeah, let's go with.
Something's not right. Try again in a little bit.
Okay, wait a bit, Cortana. I'm good. So let's use a green field, green plane, drag and drop. That's so nice with Unity. It's so easy to build that stuff. Yeah, that was funny. A cube. So we will add a cube onto our plane, like I mentioned. Also reduce the size of this one a bit, like that. And pull it up a bit. Yeah, like this. This is good. And add a rigid body component. So physics rigid body component from Unity basically tells the Unity runtime that it should run rigid body physics calculations here. And so we just duplicate this one, place the other one here, and the other one on top, like this. And then we can hit the play button and see if our physics stuff works. They should fall down on the plane once it's compiled. Yep, that works. Okay, nice. So we have our basic scene set up. Let's add some actually HoloLens functionality. So we will add another folder for that, for our scripts, basically, because we will write some C# scripts for accessing the HoloLens APIs. Yeah, so let's call it Canon behavior, because like I said, we want to shoot spheres from the camera into the scene, so like a cannon, like a cannonball. And we can attach that script to our camera. I just drag and drop it to the camera here, and you see it's attached here. And then I double click, so it opens in Visual Studio 2015. I really like that with Unity 5 they finally added a full Visual Studio support, so you can use Visual Studio for editing your scripts. And you can actually also debug your scripts, which is very nice. You just set a breakpoint in Visual Studio, attach to the Unity process, and you can debug your scripts. Very convenient if you're a Windows developer. So that's nice. And you can use C# scripting, like I said, and also JavaScript, actually. So that's nice. We were using C# here. That's my preferred language for this kind of stuff. Okay, cool. So this is the basic Unity scene. The basic Unity script. It is generated for us. We have the start method for initialization, which is called once the script is started the first time, and the update method, which is called every frame, basically. So let's remove that stuff, because I have some code snippets already prepared, which we will plug in, and then we talk about those. So let's add the gesture recognizer for the art tapping. And I have this class here, which I instantiate, a gesture recognizer. And like the name implies, this is an HoloLens specific API, which is responsible for, well, recognizing gestures. It has a few events, like this tapped event is of course fired when the user does this tap gesture. And then we can also define what kind of gestures we're interested in. In this case, we just want to listen to air tapping, to single tap. So that's fine for our use case here, but you could also set a few more gestures, of course. And then we call it start capturing gestures, which is nice because we can also start and stop this kind of gesturing, gesture recognition like we want. Okay, let's add the tapped event here. This is the event handler, which is triggered once the user taps. We call a shoot method. And what this shoot method does is it creates a sphere in code. So just like we created those cubes in the Unity editor, we can also create those dynamically in code. And since we attached that script to the camera, I thought those spheres are like you're shooting out your eyeballs, right? So that's why I'm calling the variable eyeball. So let's set the scaling a bit lower. So it's not a huge ball, but a bit smaller. And we attached a rigid body component to it as well to have rigid body physics calculations. We give it a mass, which is a bit lower. And we set the position, the initial position of the rigid body to the transform dot position. And this transform in the script is the camera transformation, since we attached the script to the camera. So the transform position is basically the camera position, right? And then we give it an impulse into the direction the user is looking. So transform.forward is the vector the user is looking. And we multiply it with a constant factor, which is defined up here as 300 Newton. And if you have never done Unity, you might wonder why I define public fields here. You will see in a second once we switch back to Unity. So let's save it here. Then we can switch back to Unity. Give it a few seconds to update. And there we go. And you see that field is now here. So this is nicely done without any attributes or something, just surface here on the Unity inspector. And they do this public fields because they also serialize it and deserialize. Cool. So this is our basic setup. Let's build it for the HoloLens. So build settings. Then we select Windows Store. Since it's a Windows 10 device, we select UWP10. We want to render DAC 3D because we want to have 3D holograms. And then we hit the build button, select a folder, and let it create the build output. And what it does now, it basically generates a new Visual Studio solution for us, which is the HoloLens applications, because the HoloLens application in the end is a UWP app. That's what it is with a DAC 3D rendering. So it generates it for us, and I did this before, so it should be a bit faster now. And I already opened the other solution. So once that is done, you will see this reload all here. So we can hit reload all and reload it. And then we launch it in the emulator. So you can select release. I usually just go with release mode. x86, because the HoloLens is a 32-bit processor, so we use x86. And then you can select the target output. So you can go with device if you have the device connected via USB, or also remote machine if you have the device. If you have an IP address, you can deploy over the air, basically. It's very nice. And we will just go with the HoloLens emulator for this case. So just hit the button here. And I already opened the HoloLens emulator before, so it's a bit faster. And you have the nice Windows start menu here. And you can simulate gazing basically with the mouse. Just left mouse button down, and mouse move is gazing. And right mouse button down is simulating an air tap. So that's very convenient. So our app launches now. And there we go. We have our cubes on the plane. And then I can hit the right mouse button and shoot at those guys. Right? But you see an issue here. It's very hard to aim. It's very hard to see where I'm actually shooting. So I don't have an indication of my gazing. So I probably want to have some indication of gazing. So let's fix that. Let's add a gaze cursor. Okay, stop it here. Switch back to the editor. Yep, yeah, all of that. Let's add a gaze cursor. Plug it in. And what I define here is another reference we will set up from our Unity scene, so we can create another game object and just plug it into our script here, and you will see that in a second. So we use another game object for showing the gazing, for showing like a cross or something you can see while basically looking at. Okay, and I will do the gaze update in the update method. So this update method, like I said, is called every frame by Unity. And what I'm doing here, I will do a raycast all, which is a built-in method by Unity. So I can shoot basically a bunch of rays into the scene from the camera position in the direction the user is looking at. And where those rays hit a virtual object, I get a raycast hit back. So and I sort those by distance, because I'm interested in the one object that is the closest to where I'm looking at. So then I get this first hit, basically. And I use that raycast hit, the position where this was hit, to set the position of our gaze cursor to that place. And also I want to orient the gaze cursor nicely to the surface of the object, so I use the raycast hit normal as a forward vector for our gaze cursor. Okay, let's save it, switch back to Unity, and add our actually gaze cursor game object. So what we will do here, we will add another cube, just a simple cube. We call it flat cube, because we will make it a bit smaller. Let's go with, like this. And this. So very small, flat cube. And you see, if we would just use the white color and on the white cubes, we wouldn't see where we're gazing. So let's add a different material to this one. And I also want to remove the box collider because I don't want to have like physics interaction with the gazing. It's just used for visual indication. Add a new material, create material red. And there you go. And just apply it. So we have our gaze cursor here. Another thing we need to do, of course, we need to add the reference here. So I just can drag and drop the game object from here to there. So our script has a reference to this game object, basically. Cool. So, but before we deploy it, I want to add some more features. I also want to add spatial mapping. So right now we have air tapping, we have gazing. Now I want to have spatial mapping. And spatial mapping is quite complex to implement. There are multiple lines you would write, and this is a session on its own, actually. But I made it a bit easier. And there's a nice project by Microsoft called HoloToolkit. It's up on GitHub, open source project, and they have a bunch of very nice scripts and a few like for spatial mapping as well. So you can just use them because someone already implemented it for you. Very nice. So I created a custom package, which I can just import here. Yep, here you go. So this is a Unity package where I just extracted the stuff from the HoloToolkit, which we are interested in, like the spatial mapping collider. And we will talk about this in a second. So let's import those. I have a prefab here. I just plug it into my scene. And this has the two scripts we're interested in already attached. And there are two scripts from the HoloToolkit, which I'm using here. One is the spatial mapping collider, which basically generates a spatial mapping collision mesh. So which we can use for physics interaction, right? So we can use the real world spatial map for physics interactions. And this has a bunch of properties, so I can say what kind of bounding volume I'm interested in, and I set it to a sphere of 5 meters. So everything that's 5 meters around me, that's what will be part of the spatial mapping mesh. Then you can also define level of detail, low, medium, and high, which basically means higher precision, but also takes more processing power, of course. And then the default for time between updates is 2.5 seconds, which basically means this is the time the spatial mapping mesh will get updated. So if lots of people are walking here by fast, they won't be part of it. But if I place the table in here and move it out, this will be part of the updated mesh. Yeah, and there's also the spatial mapping renderer, which is similar to the spatial mapping collider, but this is used for visualizing the spatial mapping mesh. And I can use material here, so I have a wireframe material attached to this one, which is just like a wireframe, looks like a net, and you will see it in a second how this actually looks like. And I could also say occlusion. So if I said occlusion, you won't see the actually mesh, you won't see the spatial mapping mesh, but your virtual objects will be occluded, they will be hidden by real world objects, right? So this is probably something you want to do. Okay, cool. So we have gazing, gestures, spatial mapping. Let's add last thing for the session. Let's add speech recognition. And we'll do this with a nice little script. So I have a C# script, another one, and I just call that one speech handler. There you go. Let's remove that stuff and plug in some code I prepared. Yeah, it doesn't. Yeah, ReSharper doesn't show me what namespaces I should add. So let's switch here and copy those in. There you go. Yeah, it's Windows speech. I always forget this one. It's Windows speech. So the namespace is here. Okay, cool. This is the keyword recognizer. This is similar to the gesture recognizer, but of course it's used to recognize keywords, right? And the nice thing is you just give it a string array, basically. So you can see I defined some string variables up here. These are just normal C# strings, right? Just a normal C# string like hide plane, shoot, reset scene. And I pass those into the constructor of the keyword recognizer. And if you have done speech recognition before with other platforms, you probably had to define some XML and a grammar and whatnot. And this is really what I like. They made it very easy. You just use C# strings, and there you go. And once it recognizes one of those gestures, it triggers that onPhrase recognized event. And we have an event handler here. And this gets in past the arguments and the text, which is basically recognized string. So I just do a very simple string compare. It's so easy. It's yeah, really simple. So I compare it with my hide plane command.
Something's not right. Try again in a little bit.
It's all good, Cortana. Calm down. So hide plane command, I can set the plane deactivated. For shoot, I'm shooting the cannon. And for the reset scene command, I'm resetting the scene. I'm just reloading it, basically. Cool. Saving it, always important to save the scripts and then switch back to Unity. We have our script here. I just attach it to the camera as well. So drag and drop. There you go. And then we plug in the references, like the plane and the cannon. The cannon is attached also to the camera, so I just attached this one here. And yeah, let's build it again for the emulator. But we will also see it on the HoloLens later. Okay, let's build it for a second. And you notice it's taking quite some time to build. Like the deployment cycle is it's taking quite a bit to test some stuff. And at the end, I will share some best practices, how you can avoid that and how you can be more productive and faster inside Unity without having to wait always for the build time and the deployment cycle. Cool. Launch the emulator again with our updated stuff. And the emulator is really nice. It's included in the SDK, and you can actually also load different spatial maps. So you have this room tab here, where I can basically load a spatial mapping I created before. So I can take the device and save the spatial mapping of a room, and then load it into the emulator. Pretty cool, also for testing. Okay, cool. So you see the gazing here. I have this little flat cube. This is now shown at the position I'm looking at, and also nicely orients to the surface of the object. I can also use speech commands. Hide plane. You see? And you see another thing. They bounce off in the real world. And if you look closely, you might be able to see a sofa here. So this is the default room that comes with the HoloLens emulator. Okay, cool. So this is the emulator. Let's do something very brave. Let's switch to the device. Ooh, and you should be able to see what I see now. Let's put it on. And you will get the code from the demo all in GitHub. So I put all the sample code up on GitHub. Good. Let's disable also audio. And yeah, there we go. Okay, let's open the HoloLens start menu. I have the finished app already pinned here. So I open it, place it somewhere like this. And then it loads. And like I said, you can get all the source code from that little demo at the end of the session. It actually also has audio collision, so we have spatial sound as well. And there you go. I have a different gaze cursor. You see, I made 2 little cubes. And I have someone else here. This is me, yes, 3D scan hologram. Yeah, I know it's weird. Yeah. And since we're in the Scandinavian region, I thought instead of shooting spheres, we'd do something cooler. So I thought we shoot some meatballs like köttbullar. Is it correctly pronounced? I hope so. So let's shoot some köttbullar. This guy, I hate him. Let's shoot him away. Hide plane. You see that? And you can all get your köttbullen for lunch. There you go. And you see them? They bounce off here in the real world, right? This is pretty amazing with the HoloLens. The HoloLens can do this spatial mapping, right? And so we can shoot here, and I can do this the whole day basically. And it's almost lunchtime, right? So who didn't have his köttbullen yet? Yeah. Okay. Cool. Glad that worked out, because sometimes this doesn't work, right, with the Wi-Fi. But I actually have my own Wi-Fi access point, so it's good. Cool. Glad the demo worked. Like I said, you can get the source code of this. Maybe not with the köttbullen texture, but with the rest, you can get all of that on GitHub later on, and you can play around with that. Cool. I also had a video prepared just in case it doesn't work. So this is the video I recorded at home. So, and you see, for this one, I actually used eyeball textures. And yeah, the nice thing is, you see how it adapts, the spatial mapping adapts to the environment. So those spheres, you see how it bounces off and rolls down the stairs? So this is recognized by HoloLens. Yeah, good fun. Okay, cool. So shooting eyeballs and Sootbollen is really, really fun, but a very small niche, right? So let's talk about some real-world applications. And we have built a couple of apps right now. So we did an engagement with a museum, so we tried out some different stuff, what you can see in a museum. So we put some dinosaur models into the office, which is very amazing, actually. Because you can see those dinosaurs at the real-world scale. And you actually can figure out, in metric space, right? So you can figure out how big they actually are. So really, really nice experience. And we also did some stuff for automotive industry, for construction as well, and plane maintenance, and a couple of other actually real business use cases. I want to spend a bit of time to talking about an app I was working on the last couple of months. It's called HoloFlight. And I want to share some best practices, some learnings and stuff with you from that applications as we build it. So HoloFlight is a real-time flight data visualization, basically. And we take the real flight data and visualize it in 3D. And if you think about air traffic controllers, what they use these days is they are looking on flat 2D screens, right? But planes and flights are actually flying in 3D. They have an altitude. So we figured let's put them in the HoloLens and visualize them as holograms. So that gives you another, relationship between the flights, because you see them nicely stereoscopic, so you get the relations between the different flights, and we can also visualize usable invisible information like flight trails and so on. Here's a quick video showing you the app. Yeah, let's turn down the volume a bit. So, what is that? Okay, that's a bit slow. What is that? Let's restart the video. Okay, that's better, I think. Cool. So you can see the Hawaiian Islands here, and we have the flight space of the Hawaiian Islands basically visualized, and you can gaze at those planes that are flying. Like I said, this is real-time flight data, and you can see flight information like call sign, altitude, and whatnot. You can also hear air traffic controls conversations and spatial sound. And we can also visualize the airport weather information, wind speed, wind direction, all of that stuff. And we use spatial mapping of the HoloLens, so the user can basically pin those information panels on different places, like on different walls, on a table and whatnot, and basically lay out the workspace. We also have different level of details for the terrain. The terrain is, by the way, built using Bing Maps API data, so this is real topographic data. Like I said, we have real-time flight data, but we also have our own Azure backend where we can cache the data, so we can play it back at different speed, basically. What you can see here, we play it back faster, and then you can see those flight trails visualized. So in flight information, you usually don't see. So that's nice, and adds another value, of course. Okay, so what were the challenges? First of all, usually flight information is visualized in 2D, but if you visualize it in 3D, you also open another dimension of errors, basically, which you don't see in 2D. Yeah, you also need to be careful with the holographic frame size, because you cannot put too much information in front of the user. Because flight information is very dense, you have a lot of information, you want to show a lot of information, but on the other hand, you need to be careful that you're not putting too much stuff there. A spatial mapping of the HoloLens, as you have seen, it's really amazing. It can scan basically the room, so you want to use that in some way in your app. Gazing and selecting at small objects like those tiny planes can be very hard to gaze at them and select them because they're pretty small. So we had to fix that as well. And you want to make it an awesome immersive experience, and spatial sound is also one important factor there. So how did we solve those? First of all, finding the right flight data. And we partnered with a company that provides us the flight data in a nice REST-based web API. So we get the data as JSON, easy, everyone can parse that. But then we noticed a bunch of errors in the data actually, which you don't see in 2D like I mentioned. For example, we had some like crazy altitude drops, like phew. And this happens just a few times, but not that often like we have seen in the data. So there were definitely some data glitches, right? Because if that happened so often as we have seen it, no one would fly anymore, right? So we had to fix that. And you can basically go with two approaches. You can do it offline, or you can do it online. Since we wanted to do real time, we did it online. So we invented some algorithms there to fix the data, to smooth out the data, to make more sense out of the data basically, and avoid those issues. Then of course you need to visualize it in 3D. So you have geographical coordinates, and you need to map that to an unwrapped planar rendering. And we also want to map the altitude. And if we would map the altitude linearly, like the 30 to 35,000 feet of flight space, we would waste a lot of rendering space with uninteresting flight information. Because the most interesting flight information is in the first like 3 to 5,000 feet close to the ground, right? So what we do, we use a non-linear mapping, basically, of the altitude. So we give the more interesting flight space also more rendering space. Then we get a bunch of positions for each of the plane in the flight space, and they can even have different timestamps, so a lot of different data, basically. So we need to normalize them so they make sense when we visualize them all together in one flight space rendering. And the right size is important, of course, because we are visualizing those planes, and if you're stepping it further away, they can become very small, so you just see a few pixels, actually. So what we do there, we use level of detail to swap out that plane model with just a cube. And you don't notice this because you just see a few pixels anyway. And we also make sure if the user steps even further away, the cube will stay at the same size. You can still see a few pixels there in the back. And you know there's something going on there. Yeah, UI, we had a couple of iterations for the UI to make sure that we are, like I said, not polluting the holographic frame, not showing too much information there. And this was the first iteration. That's my fault. That's developer UI, so super ugly. And next one was in-place billboards. So we had those little billboards which were shown directly at the plane position. So you could pin and enable them, multiple billboards basically. And you see the issue in the screenshot. You have those overdrawing, you have those overlay issues. Also not very nice. Then we figured let's use a curved screen UI, which is nice because the human head is also a bit curved. So you have all those curved TVs, right? So we figured let's use a curved piece. But this thing then kept on growing and growing. We wanted to show more information, like flight information and weather information and whatnot. So it was also not fitting the holographic frame anymore. So then we split it up, and we polished it to what you have seen in the video. And we have those independent panels, basically, and the user can pin those separately in the room, basically, and lay out his workspace. And we're using the spatial mapping of the HoloLens to allow the user to place those. Cool. Yeah, size matters also for ray casting. Like I said, those planes are very small, and if you want to gaze, if you want to select them, the gaze ray will often hit nothing, basically. So we figured let's do something else, and we use basically just a simple sphere collider. So we use a sphere collision volume, which is a bit larger, and you can also think about to dynamically adapt it. So if the user is stepping further away, you can grow it a bit to a certain amount, and if the user is getting closer, you can make it smaller, and then actually switch to the real mesh collider of the plane. The sphere collider is also a nice performance gain, because testing array with a sphere is really cheap, it's really easy, and doesn't cost a lot of performance. Yeah, spatial sound. There's some crazy experiments out there. You can see on the slide. Really, I'm sure it has a super amazing spatial sound, right, with all this, but it might also be a bit heavy on the head. So I rather prefer this one. And the HoloLens has those tiny speakers up here, right? You have those small speakers here. And of course, they don't provide a very bass sound, not very low frequency. But what it does with those tiny speakers is super impressive. It's really good. And yeah, it's perfect brain trickery, actually, because you know where the sound is coming from. And in HoloFlight, we actually use it for this.
Seabird 182 Heavy, right Mike Alpha, right Bravo, then Papa.
So we use that to play back air traffic control conversation. And those are not just adding value from the ATC conversation itself, but also from the spatialness, from the spatial sound, because we're playing back that sound in 3D at the plane position. So even if you're not seeing the hologram, like rotating your head, you don't see the hologram, which is somewhere here, but you hear the spatial sound, and your brain knows where to turn. You know where the sound is coming from, right? And this is what they have really done very nicely with the HoloLens. They have a very good algorithm there to compute those spatial sound. Really good. And if you have a use case in your applications, make sure to use spatial sound. It's really adding the topping on the cake, if you will. Cool. Some further best practices. So use fading and transitions. This is an important one, because in the real world, objects don't just appear or disappear. Maybe ghosts if you believe in such things, but I don't. So, and virtual objects, you can just enable or disable them, right? You can just make them appear or disappear. but of course you want your virtual objects to behave like real-world objects, so you need to fade them in, move them in, grow in size, shrink in size, and so on. And I have 3 short clips here where I want to visualize you the differences of all those 3 approaches, what you can do basically. And so we have all the Hawaiian islands here, and then we want to switch to just one island, right? So we see all islands, just switching to one island without any transition. So this is not very nice, very awkward. Then you could do a crossfading, like an alpha blending between the terrains. So you can do this, which is a bit nicer, it's a bit smoother, but on the other hand, you're losing the context. So as a user, you don't know where you're looking at. You don't know which island you're actually zooming into, right? You see all islands and you just see one island, but which one? So what we did in the app is basically scaling up the mesh of the all island, we're scaling up the texture of the all island mesh, and then do a crossfading to just the one island. So this is a bit nicer, and it's a nicer transition for the user to actually know where to look at then. Cool. So let's talk about my top 10 HoloLens development recommendations. First of all, you can be a really good developer. You can be a great 3D developer, best one in the world. But if you don't have any 3D content to show, well, you don't have anything to render, right? And at Identity Mine, we're lucky to have a bunch of very talented designers and also 3D artists who can make very nice and good 3D models, and also with a reasonable triangle count. And I say reasonable because HoloLens is a mobile device, right? HoloLens is a mobile device, and compared to virtual reality headsets like the Oculus Rift and the HTC Vive, with those, they are just displays basically, with a bunch of sensors. But the computing is all done on a computer, in a full-blown desktop PC, right? For the Oculus Rift, you need a really high-end PC, which of course can compute like amazing scenes, can compute really nice renderings, but you're always connected with a cable. You're basically always on the leash, right? So with the HoloLens, I much prefer the HoloLens approach because it's self-contained. Everything, this is a computer, right? It has everything inside here, and I don't need an extra cable. I can just put it in and walk freely around and can interact with other people as well. So this is much nicer, but on the other hand, you have limited computing power, of course, because you cannot put in your full-blown desktop graphics card in that device. It would probably get very hot if you would do that, and this is something you want to avoid as well. So limited computing power, and what we noticed is that the HoloLens is mostly fill rate bound, basically. So you can render tens of thousands of triangles, like 50,000, 60, 70,000. It's not an issue to render those. But if those are rendered closely to the eye, if those are rendered closely to camera and take up a lot of pixels, and you have a heavy pixel shader running for each pixel, then your performance will drop. You get really quickly running into issues there. So you want to draw your pixels very easy, and for example, don't use the Unity standard shader, because this is too heavy. It's doing too much. And what we noticed is you can actually get away mostly with vertex lighting, so you can just use a simple lighting model for vertex-based lighting and have a super cheap pixel shader. And another thing you want to avoid is like overdrawing. This is just with every mobile device basically. You don't want to have like meshes, models, multiple after one after another, which would cause like multiple pixels drawn multiple times, right? You want to avoid those overdrawing issues. Also large transparent objects are issues. So you need to be careful there, because you want to render with 60 frames per second. This is really important to render your holograms with 60 frames per second. Otherwise, if they're dropping to 30 frames, they can become unstable. So you have seen they're pretty stable in the room, right? Even if I turn my head, they will be at the same position. But if the frame rate drops, they can becoming unstable and drift. And this can make users sick. Actually, Microsoft did some user research there, and some people really get headaches and they can throw up. So you really want to go with 60 frames and optimize everything. Still, the HoloLens has a multi-core CPU, and in HoloFlight we use that for the data fetching, the data clearing, and all the processing is done in a background thread basically. So we can keep the UI thread free from that work, and UI thread can keep up with the rendering loop. Yeah, if you have never done a 3D programming, or it's been a while, you probably want to brush up some of your math skills. As you have seen, there's a bunch of stuff going on, like with vector algebra and so on. You don't have to implement all yourself. Unity or whatever game engine you're using is helping you a lot. They have everything built in, but of course you need to be familiar what that means. what is a transformation, what is a matrix calculation, right? So this is important. Anchor your holograms. So the HoloLens has an API which is called World Anchor. And if you remember the demo, I grouped those cubes and the plane in one container, right, in the scene hierarchy. And what I could do, I could apply a world anchor to that container, and then the HoloLens runtime would basically give that world anchor its own coordinate system, right? It has its own coordinate system, which then results that the HoloLens makes those world anchors very stable. So even if I leave the room and come back into the room, the HoloLens, the holograms will still be at the same position. This is done with the world anchor, basically. And the coolest part about it is you can actually persist those. So you can save them in a global storage in the HoloLens. You can save the world anchor with an ID. And once you reload your app or restart the device and then load the world anchor position, they will be at the same location. And when I'm flying back home, hopefully tomorrow, I don't know, I heard some really interesting things about a strike or something. Well, and if I'm flying home, hopefully I will see some holograms in my office at the same position when I left them. So this is done with the persistence, right? So you can persist those world anchors. Pretty cool. Yeah, leverage level of detail. Like you've seen, you can save some rendering time there as well. You don't need to show the high detailed model when it's just like meters away. Yeah, the gaze cursor is important. As you have seen, like that main input paradigm of the HoloLens is gazing and gestures. So you want to make sure that your that your gaze cursor is very stable and very nicely done, because the user will see that most of the time, basically. And one part about it is to smooth it, basically, because the gazing is based on head rotation, right? This is based on the IMU unit, which means this is based on sensor data. And like every sensor in the world, this contains noise if you use the raw data, which makes the gaze cursor jitter, always slightly move. And this is something you want to avoid, right? You don't want the user to like always have this jittering thing in front of it. So you would want to smooth it, basically. And the Holo Toolkit I mentioned, it has a bunch of reusable scripts and also a smoothing algorithm implemented. So you can use that one. We actually developed our own because it gave us a bit better results with less lagging. It's a bit faster to react. Also, the one we implemented has some prediction. So that's just giving us better result. Another thing about the gaze cursor is the hand-ready state. So the user is air tapping, right? And the cameras of the HoloLens, of course, need to see the hand. So if the user is air tapping here, it won't work because it doesn't see the hand, right? It needs to see the hand somewhere here or there, also works, but not there. So you want to give that feedback to the user that it's now basically seeing the hand and it can interact with the piece the user is gazing at. And what most apps do, and also the HoloLens start menu, they show an open ring gaze cursor when the hand is in view to tell the user, okay, you can now interact. And they show a flat circle, something like this, when the hand is not in view, right? To give the user the information, okay, open the cursor, you can interact. The other cursor, nope. Those details really matter. They make out a good experience, and you probably want to have a good experience. So pay attention to those details. Yeah, use animations and transformations to let your virtual objects behave like real world objects. And yeah, so this is also a nice one. So if you have a bunch of Unity projects, you probably also have a few reusable scripts. And the naive approach would be to copy those script files between all the different projects. But this is not nice, because when you have a bug or something, or want to change something, you have to copy all the stuff. So what I did instead, I created a central C# solution where I have all the reusable scripts in one central place, basically. And I can just then build out a DLL and copy that into a special folder into your Unity project. So the Unity project have that assets folder, right? And there's a special folder you can create, it's called plugins, where you can put in DLLs. And then you can just reuse those scripts as well from the DLL. And this works out quite nice, because I also have a post-build step in my C# solution, so I just hit build, and all my projects are updated with the latest stuff. There's one gotcha. The Unity editor uses mono runtime, which is actually a 5 or 6 year old version of the mono runtime. So it's quite outdated. I think this is being fixed now since Microsoft acquired Xamarin. So I was at the Unite conference last week, and they basically announced that on the roadmap that it's planned to update the mono runtime they're using inside Unity, which is great because you don't have TPL or anything in the Unity editor, right? You don't have task parallel library. So, but on the HoloLens, it's running Universal Windows Platform. So it's running UWP.NET Core, latest one. So what I have to do is basically have two C# projects. One I'm building for the for the Unity editor, mono runtime. The other one I'm building for UWP. And I'm just sharing the scripts. And sometimes you have some precompiler directives like if Unity _ editor, blah, 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 do this, right? Those kind of things. But anyway, having this central C# solution with all the scripts in one place really is a huge benefit for maintenance. Yeah, avoid the long deployment cycle. As you have seen, it's taking quite some time to deploy something to the HoloLens. So first of all, you need to change your Unity scene, then build the Visual Studio output, and then build it again, and then deploy it to the emulator or the HoloLens. So this is really, if I want to test some small stuff. And what I did here, I wrote a custom script where I can simulate the gazing and gestures already inside Unity. So I can do the same like the emulator does. I can use my mouse for gazing. I can use the right mouse click for air tapping. I can also use different gestures, but I can do this already inside Unity. And for every little change, I don't have to deploy it to the device or the emulator. It's a huge, huge time saver, right? So the HoloLens also has a bunch of other gestures I didn't mention, like the air tap I said, then it has double tapping and tap and hold, so you can do like scrolling. The nice thing is three-dimensional, right? Not just this, but also like this. So those gestures I can also simulate already inside Unity with the custom script I wrote there. Yeah, so you can stay productive most of the time inside Unity. But of course, you also want to test it on a device if you're lucky enough to have one, because nothing comes as close to this device as the real device itself. The performance and spatial mapping and so on. But anyway, the emulator is really good. As you have seen, it supports speech recognition. I can load spatial mappings. I can basically test most of the stuff already with the emulator. Cool. So I think next chapter of computing is really happening right now, and it's a great time to be a developer. And it's really good to be working in that space again. Yeah, and the HoloLens is one of its kind, I think. We have a bunch of virtual reality devices, and the HoloLens is often compared to those, but it's actually, of course, it's not a VR device, as you have learned. It's actually a mixed reality device, so totally different. And it can also do things which are just not the difference in showing the rendering of the pieces, like augmenting the real world, but actually it can do the spatial mapping, for example. You can have the collaboration features and so much different things. And I'm pretty sure the HoloLens, it will change how we interact with computers. It really has huge potential. And you can even run 2D apps on it. So you can develop the Universal Windows Platform applications, and they will also run in the HoloLens. But they will run in a window, basically. So you can have a 2D window, then you can pin it here or there or whatever. It's also nice. But of course, with a stereoscopic 3D rendering, 3D is king, basically. So you want to have 3D content. And you can do this with going straight with Direct 3D 11, which we also do, by the way. Or you can use Unity, right? And Unity is a nice tool. You can get quickly started, be very productive. And there's a use case for every piece, right? For example, I wouldn't build Skype with Unity, right? I would build it straight with Direct 3D and C++. That's for sure, right? But for really nice proof of concept, Unity is great. And not just for that, like I said, a bunch of HoloLens applications in the store built by Microsoft are actually built using Unity. Yeah, you can get a few links here. So the HoloLens SDK, you can download it for free. It has the emulator inside and also the special Unity build that is supporting HoloLens development. Holo Toolkit for Unity is also available. On GitHub, it contains a bunch of scripts, prefabs, shaders. So they actually have some nice optimized shaders you can use, like for vertex lighting and so on. Pretty good stuff. So you really want to grab a copy of this one once you install the SDK. And yeah, on my blog, you can find the top 10 development recommendations, a longer write-up with more details. And also the slides and the demo code. I will put the link for the demo code on my blog as well. And the demo code is actually on GitHub. Cool. So we just have a few seconds left, and I don't want to overrun, because there's lunch, I think. So we're all hungry The Shotballen was just holograms, so they weren't real. Hopefully they have some real ones. I need to try them. Anyway, so you can shoot me an email or tweet to me, or I will stick around here a bit and just ask me there if you want to ask some questions. And with that, I thank you for attention.